Hello, the topic of this talk is Mem2Img, a memory rather than malware detection via convolution neural network. Memory injection is a technique often used by modern malware to bypass detection. It has become an headache for security products to defend against this kind of malware. In this talk, we propose this framework to help us detect and classify memory rather than malware. Aragon is a malware researcher in Team T5. He will walk you through the details of this work later, and I'm Charles, the chief analyst of Team T5. Both of us are dealing with various malware in our daily job, and we are trying every possible way to improve our malware detection capability. Thus, this work. The agenda of this talk. In the beginning, we will show you some recent injection techniques used by APT attacks. The main part is the data set and the framework, the experiment result of this framework. In the end, we will talk about the salience map, zero-shot learning, and adversarial attack about this framework. Memory injection technique is popularly used by malware to achieve malware results. Before start of this talk, we will discuss some novel technique to achieve injection that might not be easily detected. The first technique we'd like to introduce is UUID shellcode. This technique was first observed to be used in the wild by Larus, an infamous North Korean APT group. Its implementation is fairly simple, using API function UUID from string to encode the shellcode to bypass security product detection. There are two advantages by using UUID shellcode. First, by providing a shellcode to heap address. This function can be abused to both decode and write the data to memory directly. Second, abusing callback function, such as in new Windows, can lead to shellcode execution. Both are typical checkpoints of security products for defending against memory injection attacks. There are many alternative ways to utilize the callback function. For example, in new system language group, in this case, we'll take the address returned by heap alloc, and it will execute the shellcode. The second technique we will introduce is phantom halloween. Typical injection often results memory blocks with rewrite execute privilege. This feature is utilized by security products to detect possible injected memory attack. However, phantom halloween can effectively bypass this detection mechanism. The code in the provided screenshot can be found in a public GitHub page, but we have seen various Chinese APT groups, including APT27, Winty, etc., to abuse this attack in their real-world attacks. This photo shows the workflow of the phantom halloween technique. The essence of this technique is to find a target DLL in system directory whose .txt section is big enough as the host of the payload shellcode. The injector component will call anti-create section and provide the flag sec image as its parameter. This results the initial privilege of the mapped section to be rewrite execute. The payload code can then be copied to the target memory area. Further call to anti-protect virtual memory to change the memory privilege can effectively bypass detection. This photo shows the result of the technique. The payload implant has been injected to the .txt section of the AA-client.dll, but the debugger information shows its privilege to be only execute and read. Next, we are introducing some novel shellcode-related technique abused by Waterbear. It's an infamous rate tool used by a Chinese APT group. Their first technique is to wrap their shellcode in some random generated data to thwart static shellcode analysis. Before preparing the real shellcode, the loader first generates two numbers indicating the length of padding before and after the shellcode. Finally, it decodes the shellcode and writes the result to the designated location between the padding data. This padding makes finding the shellcode more difficult and may help avoid detection. After writing the shellcode, the loader starts a thread using beginThread.ex function. beginThread.ex acts as a proxy here and starts the new thread at the thread.ex, another function provided by C library, instead of the address where the shellcode is located, as if using create_thread directly. This makes the shellcode less detectable, as some antivirus software checks whether the entry point of the thread locates in a manually allocated memory. The dataset overview of the machine learning. Before experiment, we prepare totally 21 malware family. They are actively used by APT group in Asia region, including APT32, APT37, APT10, APT27, Winty, etc. We also include some cybercrime malware families, including Imitate, Phonebook, Redex, etc. Before doing experiment, we use tools such as PECIF, Volatility, and HoloFind to help us find and extract malware in memory. Our data source, including data from real victim computer. Also, we try to do tri-edge to find more related samples on VirusTotal or online sandbox. This is the file distribution for totally 30 malware family used for training. The biggest category is cybercrime malware. They have around hundreds of memory blocks. However, for some malware in APT, some has only tens of memory blocks. You can see some imbalance for the dataset. To address this issue, we use some typical methods such as class-wise, smart, data augmentation, transfer learning to help us to address this issue. Why do we choose transfer learning? Because some APT memory raster malware is only a small set of data. Transfer learning uses knowledge from a learned task to improve the performance on a related task. It typically reducing the amount of required training data. Our framework will transform the malware binary to an image for classification. Before introducing our framework, we would want to show you some generated photo to give you a feeling. And also this. For some malware families, for example, Dennis Redex, the generated photo looks fairly similar. However, the generated photo could look very different for some other families, such as CobbleStrike, Stager, Imitate, etc. We will show you our framework can effectively classify this malware.
This part, we are going to talk about the Mem2Img framework. The first step is to pre-processing the data. There are some continuous strong bytes padding at the bottom or the beginning of the memory blocks, like the picture shown on the slide. It must be removed to avoid the model learning those strong bytes of the features. In our dataset, they often have null bytes or hexFF. Here is to talk about how we convert a 1D array to image. The malware is a 1D array. First, we convert the binary to decimal value. and count the square root of the length of the 1D array as the 2D array's width and height. And with this 2D array, we can convert it to a grayscale image like the image in the slide. So the size of the image is determined by the length of the malware. We construct RGB image to represent a malware memory block. The red channel is the decimal values of each byte, also can seen as the grayscale image from the slide. The green channel is composed of local entropy values of the image. We use the entropy function by skin image library to count the value. The local entropy can show some complexity relationship contained in a given neighborhood. The filter returns the minimum number of bits needed to encode the local grade level distribution. The disk is set to 10 in Mem2Img framework. The blue channel is composed of channel entropy values of each byte. These are schematic diagrams of the three channels. Red channel is the grayscale image composed of decimal values of each byte. Blue channel is the local entropy. If one area is encrypted, the entropy will be very high, and the model may not use that area as a feature. The output image of the channel entropy of each byte is very similar to decimal values in red channel, but they are still a little different. We won't use this channel to increase the inference of bytes value instead of using the same value of the decimal again. This is a schematic diagram how we generating the RGB image. The red channel and blue channel can directly come from binary value. The channel entropy values are between 0 to 1. So we multiply the channel entropy value by 60 to increase the influence of the channel. The green channel is the local entropy value of the image. We first convert the binary to grayscale image and generate a local entropy image, and put each byte's value of the entropy image to the green channel. And we also multiply the local entropy value by 50 to increase the inference. Local binary pattern is an efficient texture operator which labels the pixel of an image by thresholding the neighborhood of each pixel and considers the result as binary number. It can represent the texture of the image. So we also used LBP as features in our framework. This slide is to talk about the theory of the local binary pattern. I won't go into details here. And we are using circular LBP, but we will rotate the picture during data augmentation. As you can see in the picture, the LBP value will change during the rotation. We will explain how to solve this problem in the next slide. To make sure the invariance, there are another feature called LBP rotational invariance. If we got a value via circular LBP, and it will try to all possibilities in any angles, and choose the smallest one value as a local binary pattern value. We use data augmentation technique to generate more data for training. We flip the image, random rotate, and random scale the image. The data amounts may be 4 times to the original data after augmentation. Here is the first part of the Mem2Img framework. First, we convert the malware map binary to RGB image and resize our image to fixed size. And why the size is chosen to 224? Because this size is the input size of the VGG16. In the beginning, it just for convenient, and after the experiment, the size also performed the best result. The next step is feature extraction. We use VGG16, Inception v3, and one pre-trained CNN network, and the output size is shown in the block. Additionally, I also add the local binary pattern as a feature. The weight in VGG16 and Inception v3 we use is ImageNet, and the weight of the CNN is trained on 30-class malware family. After feature extraction, the feature fusion step combines the 4 features to one array. Because the dimension after feature fusion is very high, as you can see, is 94,000. So we use PCA to reduce the dimension. After keeping 95% feature which is important to the model, the dimension is reduced to 1000. And last, we use logistic regression to train the model and make the prediction. Here is the architecture of the pre-trained CNN. There are 9 convolution layers and 2 max-proof layers. We also use some dropout layers in this CNN network. We split out the data to training and testing. The proportion is 5:1. The task is a 30 malware class classification. There are 12,569 memory blocks, and the amount is after the data augmentation. And the activation function in the CNN is ReLU. And we also use spatial normalization and learning rate cat in the CNN network. And the training epochs we set is 32. This table is the experiment result of different features. The first one, Mem2Img, uses all the feature extracted from 3 convolution network and the LBP. It has the best result. If we only use CNN to extract features, the accuracy is about 96%. If we only use VGG16 with the ImageNet weight, the result is surprisingly high as the CNN, and so as the Inception v3. And if we only use LBP features to training, the accuracy will down to 84. And here are the experiment results for different forms of the image. If we use all the 3 channels, the accuracy is the best. And if we just use red channel and blue channel without local entropy feature, the accuracy will down to 92%. If we only use decimal value as a grayscale image, the accuracy is down to 88%. So we can conclude that local entropy can effectively help improve the accuracy. Here are the experiment results for different algorithms. The results of logistic regression and SVM are both great, and we choose logistic regression in our framework because the computing cost is less. The performance of XGBoost and random forest are not as good as the other 2 algorithms. From the confusion matrix, we can see that most of the categories can be classified very well. Only 4 types of malware that have misjudgment. Among them, there are 1 categories that have significant errors, as you can see in the picture on the right side. The 2 categories are Poison Ivy and the Poison Ivy variant, Phamtom Ivy. Our model may recognize the common area of the Phamtom Ivy and Poison Ivy. So for some malware variants, our model may not be able to classify them very well. This is the TSNE for the invading after PCA of 30 malware family. There are 2 interesting areas. The first one is on the right. We can see that the malware embedding used by APT group are very close, like Capture, Keyboards, and Waterbear. It means that the malware used by them have many similar characteristics. Maybe we can use this phenomenon to attribute the malware to APT group. The second one is in the left. We can see the CobbleStrike beacon, the CobbleStrike stager loader, and the CobbleStrike beacon variant are also very close. So it means that our embedding can make the malware variant close to the original malware family. This feature is helpful to recognize new malware variants and inspire our zero-shot learning we will talk later. A saliency map is an image that shows each pixel's unique quality. We use it to indicate which pixels are more meaningful or important for each model to predict results. So more light area is more important. In this slide, we can see that our pre-trained CNN may obviously focus on certain area and the area which BGG16 and Inception V3 focus on are more divergent. Poison ivy and plugs also have similar characteristics in Saliency map. From these four categories, we can see that BGG16 will pay more attention to some places on the edge of the picture, and Inception B3 will pay more attention to center area of the picture. If you look a little more closely on the Saliency map, you can find some interesting phenomena. For example, the focus area of the Waterbear is the config block of the Waterbear stager. And for the capture loader, the focus area is in its RData section. And for Phamtom Ivy, the focus area is some shellcode snips in his block. We also use this shellcode section in YARA rule to detect Phamtom Ivy. For plugins, the focus area is the section which the stack string located. Grad-cam has some similarity with Saliency map. We also use this method to realize how our convolution network learned from the malware image. More red area indicates that area was more important to that class. In JADEX, on the top red area is a C2 parsing function and API spam bypass function. And the second red area is composed of some code function before our data section. In CoverStrike Beacon, red area is part of our data section and part of data section. In dpass loader, the red area are some unique strings block shows on the right. In phonebook, the red area is some obfuscated stack strings. And when we want to detect unknown malware didn't in the training class, we can use zero-shot learning, which also use Mem2Img to extract embedding and then use KD tree to find 5 to 10 nearest neighbors in our dataset. For example, if the nearest neighbors are TS cookie and keywords, we can speculate that unknown malware may be modified from TS cookie and maybe have high connection to the pre-empty group. And when we input the same unknown malware into Mem2Img next time, the nearest neighborhood may be the unknown malware input last time, and they can be new class when they have reached a certain amount. It didn't need to retrain a new model. That's fantastic. And here are some zero-shot learning results. We test some AVT malware didn't use in training dataset. Jinko Spy is a new malware used by AVT37, and we can see that the nearest neighbors are Rock Raid, which also used by AVT37. And plug-S fast version and other plug-S variant also shows good results on zero-shot learning. Another interesting thing is that there are new malware called frame catcher named by us. We can't really attribute the malware to an empty group, but through the zero-shot learning, its embedding is very close to the Selena rate. So we can speculate that frame catcher may be related to the actor behind Selena rate, which was Tidal. Machine learning model is inevitably to adversarial attack. So we also think some possible attack methods to this framework. First, actor may paid in much random drunk bytes to make the file size very large. This way, may affect the resolution of the image, and then our framework can recognize the real malicious part. The second way is that deliberately put the code of other malware family into the original malware for obfuscating, and then our framework may have misjudgment. We have also seen some actors make peg file in memory using UPX and VM-protect. The last method is self-modifying code. It can alter its own instruction while it is executing. We have simply used this technique in their malware. Waterbear usually use self-modifying code. The shellcode will decrypt the code that is needed and encrypt the code that is not needed while executing, and repeat this action continuously. Such mechanism may be able to bypass our framework. For example, you can see that only the function waiting for the connection will be decrypted during executing, and the others are encrypted after self-modifying code. And here is our conclusion. More and more advanced methods of process injection have been used in APT groups and cybercrime malware. Transfer learning have great performance on memory-resident malware classification, especially on small set of data. The features extracted by a convolution network can find out the spatial area of malware which unexpectedly overlap with some YARA rules we wrote to the malware family. With zero-shot learning, we don't need to retrain the model frequently. We also propose some attackable methods for adversarial attack. And the Mem2Img framework will put on the GitHub. So if you are interested into this framework, you can go to GitHub. And here is our talk to the Black Asia 2021. Thank you, everyone. If you have any questions, it's welcome to contact us.